Yes, so Blacoh Industries, um, we are talking about the importance of transient pressure monitoring. Thank you for joining and giving us your time and attention. We will go all the way from theoretical to practical. Um, so if you are one of those very cool people Amy Marroquin referred to in the previous Blacoh webinar in this series as having a hunger for more water hammer detail, you've come to the right place. We'll dive a bit deeper into some aspects of water hammer, such as breaking down wave speed further. We'll answer what transient pressure is and why it needs to be monitored by first reviewing definitions we learned. Then we'll review some theory of transient pressure and waves to give or refresh your understanding. This background will help in understanding why transient pressure monitoring is important. Then we'll discuss practically how and where transient pressure monitoring is typically measured. Finally, Calvin will show real data taken from the field and reveal the valuable lessons learned. Slide, there we go. Just as a review, if you attended our previous webinar, or if you're just jumping in, brand new, what is water hammer? Water hammer is an acoustic pressure wave generated by a change in fluid velocity. It can be caused by, that means it can be caused by anything that changes velocity. So pump starts or stops, changing the speed of a pump if it's a variable frequency drive, if you stop one pump while others are operating, if there's a power failure and all your pumps trip, whether that's intentional, well, power failure is accidental, but power pump trips, intentional or accidental. Valve closure or opening, even slight closures or opens can be enough to impact your system negatively. Check valve slams, air valve slams, those can be caused by other causes due to water hammer and then cause secondary water hammers themselves. So what does this impact? Really, anything in the system, pumps, pump impellers, uh, the body of the pump itself, pipe walls, they can collapse. The supports because they're holding up the pipe. Valves, we've seen valve bodies completely break apart from water hammer. Seals, instrumentation, anything in the flow path. So some other terms that we'll be using interchangeably with water hammer are acoustic pressure wave, shock wave, hydraulic transients. Having trouble changing my slides. Okay, there we go. Um, so while water hammer is a phenomenon in the sense that it's a physical event, typically occurs outside of our perceived normal life, it's actually quite common and goes unnoticed most of the time. Whether we hear the audible hammer sound in the pipes or not, these pressure waves from any change in velocity are flying around in our piping systems all the time and can greatly vary in magnitude, and they can either be positive or negative. So because of how fast water hammer occurs, it often goes unnoticed, and because it's not understood, it's only sometimes suspected after a failure occurs. We tend to suspect malfunctioning equipment such as stuck air vacuum valves, relief valve, check valve, when actually the wave passed by the valve much faster than the valve could react. We don't have widely used equipment installed to properly detect transients in our piping systems yet. Transient flow is any flow that is not steady with time. It's the intermediate stage flow from one steady state to another. That's the definition given by Chaudhry in his book, Applied Hydraulic Transients. For example, when the pump has been running a while and no changes in the system are occurring or have recently occurred, you can be said to be in steady state. When the pumps trip or a valve opens, closes, or even partially closes, flow is altered, which induces a pressure wave, which is eventually settled out in the system by friction and the damping effects of water, which brings the flow to a new steady state. The flow in between steady states is called transient flow. Transient pressure is simply the system pressures incurred during transient flow. So, why we are measuring pressure and not flow? Instantaneous pressure is easy and cheap to measure at high frequency. My coworkers, my coworkers and I even have the equipment installed on our home washing machines. Flow can be measured, but it's not ultimately what we're looking for. It's like an intermediate parameter. Pressure is the parameter that gives us the more useful information. We want to verify our pumping system is operating safely and as intended. If design flow rates are exceeded, and even if erosional velocity is reached momentarily, it's not usually as concerning as if design pressures are exceeded. And those can be high pressures or low pressures. As mentioned earlier, other terms often used interchangeably: surge, water hammer. A couple others are transient events and transients. The transient pressure response from initial change in velocity is characterized as a longitudinal compression wave, much like pulling or compressing a slinky. In general, the wave travels through the piping system until it reaches a boundary where it changes sign and direction. The wave comes back to its originator and oscillates back and forth until it gets dampened by friction. It's not a bulk wave where mass is actually transferred with the wave itself, such as with waves at the surface of the ocean. It travels much faster too. It's like a very, very fast acting slinky. As you may remember, Joukowski's instantaneous water hammer equation describes the pressure response to a change in velocity as being dependent on two other variables: fluid density, rho, and wave speed, c, also called celerity. The speed at which wave travels is the speed of sound of the piping system. Wave speed is a function of the compressibility of the fluid and elasticity of the piping system. This can easily be around 3,000 miles an hour in many systems. The numbers shown here and on the chart are for a 6-inch line carrying water. So you have PVC at the lower end, around 800 miles an hour, ductile iron and steel at the higher end at almost 3,000 miles an hour. And for reference, the sound barrier is 1125 feet per second. So we're talking about these waves going through our pipe 4 times the speed of sound through air. This is why whales can communicate to each other from miles away. So here's the equation for wave speed. Elastic modulus of the fluid is this E sub F here and here, and the elasticity of the pipe is the E sub P. Those are kind of like the spring constants. Other parameters include rho, the liquid density, K sub R, the restraint coefficient, which describes how well the piping is supported and restrained. You also have D, the pipe diameter, and T, pipe wall thickness. So For example, if you have a larger E sub P, which is like I said, like the pipe's spring constant, this term down down here is larger. This whole term gets smaller, which makes this whole term larger. So hence, if you have a stiffer pipe, you have a faster wave speed. So you may say, but can't you just simplify the pipe as being perfectly rigid? And isn't liquid an incompressible fluid anyway? Well, even in hydraulic analysis applications, steel's slight elasticity does come into play, and water is very slightly compressible. Energy is lost in deforming the pipe, which will lower the wave speed. Air entrainment can significantly affect the fluid modulus also. These variables, all these variables need to be taken into account when making an accurate hydraulic model. However, practically, especially in the design phase of a project, they can only be estimated. So, after giving you an idea as to how pressure waves are induced and how they travel, let's talk about how we can monitor them. What we mean by transient pressure monitoring is measuring and recording pressures at a scan rate high enough to capture the full extent of transient pressures incurred at a specific location. We want to capture enough data points that we are confident that we have characterized the wave. Transient monitoring devices, sometimes called data loggers, are used for providing additional pressure information than other options such as pressure transmitters, pressure transducers that are hooked up to SCADA typically, um, capturing the pressure impact from events such as pump trips, valve closures, etc. We can tell how high or low the pressure was, what the effect these actions had on nearby piping and piping miles away. Remember, the wave may travel 3,000 miles an hour, which means it won't take long for the opposite end of the system to be affected. In fact, when you place multiple devices or sensors at unique locations in your piping system, you can have an even clearer picture of what happens and what affects different components, such as check valves, relief valves, or surge vessels, have on the pressure wave, as opposed to just using one sensor at a time. Now, armed with the whole pressure timeline, you're able to do root cause analysis if there's a failure, whether minor or catastrophic. For example, triangulation can be used to determine where the wave was originated from. Once the culprit is identified, then mitigation methods can be accurately proposed instead of just coming up with a band aid solution. Like, did that pipe main from the 50s break due to water hammer? Now we can tell if water hammer was a contributing factor besides just blaming the failure completely on rust and corrosion. You can also use transient pressure monitoring to tell how safe it is from a pressure and fatigue standpoint to operate the existing piping setup, because you can actually detect every cycle and their pressure limits. Finally, and ideally with an adequately designed system, you can use transient pressure monitoring to verify and calibrate your computer model or hydraulic analysis, since real variables such as wave speed that we talked about before, material properties, pump and valve characteristics, these variables are only estimated. And don't forget the big unknown, air entrainment. You can use transient pressure monitoring at two different locations to measure the wave speed, and you can adjust your computer model accordingly. So here's an example of transient pressure monitoring. It's a visual recording graph of 5 minutes worth of data of steady state and transient pressures. When the thousands of data points are arranged together, they give you not only a good overview of the pressure ranges, but also a detailed view of each pressure oscillation. For example, you can zoom in on the operations here to get this graph of 37 seconds. And then even further, if you want to zoom in here to the first oscillation, you can get this graph of the 5 seconds. Um, the red data shows the pressure transients, while the blue data is showing the steady state pressures, where the pressure is not changing. Without high frequency monitoring, you may be able to determine steady state pressure accurately. That is, only if you know you aren't in the middle of a transient event, but you really only have a handful of the thousands of puzzle pieces that make up the whole transient puzzle. To make it easier to understand, here's a correlation to shutter speed. The cars in this picture move from point A to point B in the same amount of time as the exposure time of the camera taking the photo. We have essentially two positional data points and the path or blur between them. What we don't have is information such as velocity or acceleration. Also, we assume the cars moved based on our understanding of the real world because we've seen how cars move in the past. We have an idea as to the tendencies of the real world, or in the case as Waterhammer, we may not. Which is to say, we don't know what we don't know. In either case, we at least know we need more data to accurately define and be confident in our understanding of its real behavior. Because somebody else has measured the same sort of activity for Waterhammer at a high frequency and got much more detailed results, we at least have an idea of what we don't know. With sufficient data, we have confidence in our measurement of the actual surge pressures, high and low. Because remember, low pressures can be just as dangerous as high pressures. When we are confident in the max and min pressures, we can verify the operating conditions are within the design allowances. For example, let's say that our allowable pressure is 200 psi. We don't want our operating pressure to exceed this. Let's say we also don't want to operate the system in vacuum conditions. Thanks to transient pressure monitoring data, we can reveal instances of breaching these allowances and by how far. When this data is overlaid with what operation occurred at the time, such as starting a pump or closing a valve, the cause of the overpressure or vacuum condition can usually be identified. Once we know the origination point, operational changes can be considered that can mitigate the effects of the wave. For example, a VFD pump can control its ramp up and ramp down time to lessen the change in velocity. Excuse me. If the wave is induced by closing a valve, valve can be controlled to close slowly. Typically, this can be accomplished by closing the valve quickly for most of the travel, but closing the last bit of travel very slowly. However, many times these operational changes are not favorable or do not sufficiently mitigate the effects of Waterhammer. A precharged surge vessel can be added to the system, or usually teed into the line, to act as an immediate source of energy or as a place to accept energy as needed. Transient pressure monitoring can also give us an accurate count of the number of pressure cycles. This information can be used for fatigue calculations and to predict remaining life of piping and equipment. As you can see in the graph, when our sampling frequency is not fast enough, multiple cycles are completely missed. So in this chart, the red line is the pressure at 1 hertz, or it's read once every second, and then the blue is read 100 times per second. Also, the highest of the highs and the lowest of the lows are missed. The space in between the data points are estimated to be linear, which is like the blur you saw in the traffic photos with slow shutter speed. A rate sufficient to characterize the wave for most pumping applications is 100 hertz. Now, let me introduce you to our friend, the surge wave. It's Blaco's transient monitoring system. We have two data logging device versions, the Guardian and the Defender, each with their own strengths. Perhaps the main difference between the two of them is in how they save data. The Guardian saves data locally on an internal USB drive. The Defender, which is on the right, saves data to the cloud via a cellular signal and is viewed at any time from a web app or mobile app. As we saw on the previous slides where we were zooming into the data can be categorized as steady state data or transient data. Both of these devices watch the data at 500 to 1000 hertz to see which category the data fits into. They record pressures in steady state mode at a typical rate such as 1 hertz per second. Once a threshold is reached, or a set amount of pressure difference in a set amount of time, it goes into what's called transient mode and starts recording at high speed, or 100 hertz. This categorization makes it much easier for our devices to save and manage the data that we want to see. We've discussed what transient monitoring is and why it's important. Now let's discuss how it's accomplished. So Joukowsky himself generated what he called shock diagrams. This is fascinating. Uh, he he did these shock diagrams, is what he called it, pressure change with time, using his analog setup in 1897. He had one Crosby indicator apparatus at 3 different locations on the tested pipeline. A spring-loaded cylinder would move a pencil 3/4 of a millimeter for every atmosphere of pressure change. The paper band was fed, quote unquote, fairly smoothly by a loaded mechanism, while a half-second pendulum marked the time on the graph with dots. It's fascinating to me that he was actually able to observe and record this phenomena he called hydraulic shock without any modern equipment. Thankfully, we now live in the digital age. Pictured here is a couple of typical setups used to measure pressure at a high frequency. The equipment used includes a pressure transducer or sensor installed in the piping at the point of interest in the piping system, either directly or with a protective diaphragm seal if the media is not compatible. Any small tap, such as a vent, bleed, or drain port, can be utilized. Often these are located near the problem valve or component for which we want to record information. Pressure sensors with sufficient update time can be used as long as they are selected with appropriate pressure ratings, explosion proof rating, etc. It can be set up to record at different scan rates. As we discussed, they use different storage methods, whether that's local or to a cloud. They can record data from multiple sensors, like our Guardian can do 8, I believe, and our Defender can do 2 sensors at a time. The appurtenances of the monitor may include a power supply, cellular antenna, and the cloud or laptop itself for storage. Then, of course, there's a software required to read, manage, and report the data. They can be set up to give alerts, perform time synchronization via GPS or cellular communication. They can give location via GPS. They can be powered by battery or with low power and battery backup in case of power outages, since power outages themselves can cause transient events. Since the equipment required is minimal, it can be easily installed just about anywhere, not just on this quarter-inch tap on a control valve, but anywhere there is a concern or a potential velocity change due to flow restriction or alteration. Ideally, you want to install the monitor as close as you can to the component that you think you might be causing the pressure wave. Or if you know the culprit already, you can place the monitor as close to the expensive equipment that you want to keep protected to see if the actual pressures are safe. You can place them on the suction of pumps to check whether the required NPSH is reached and to detect cavitation. You can place them on the discharge of constant and variable speed drives to verify the pump curve and its performance, and to detect flow reversal. If you are pumping in series, you can place one on the discharge of the booster pump and upstream of the mainline pump. You can measure the actual check valve closing time and detect the magnitude of the pressure spikes due to slam and whether any secondary water hammers were induced from the slam. Pump and valve characteristics, such as closing time, are sometimes unknown during the design phase, and even sometimes still unknown after valve selection. Transient monitoring can measure these important pieces of the hydraulic puzzle. You can measure the pressure drop across cross-connection control devices. You can place them upstream and downstream of long runs of pipe to confirm wave speed and to detect line breaks. You can use transient pressure monitoring to verify the functionality of and to fine-tune pressure control and flow control valves. Although this list is not exhaustive, it gives you some ideas as to the diverse usage of transient pressure monitoring. A single monitor can be placed on the inlet of air vacuum and pressure relief valves to verify they are operational during transient events, to detect the event itself, and to make sure there is no slam or chatter. It has many uses on pulsation dampeners and surge vessels. It can be used to verify pre-charge pressure on bladder vessels, which is the pressure the vessel is brought to or charged to before it's brought online. If it's used with another pressure device on the air side, the differential pressure will tell you the liquid level, which for bladder vessels tells you whether the bladder is positioned safely. It can verify the performance of the dampener by measuring residual pump pulse. You can tell whether the vessel sizing is correct when intentional pump trips and valve closures are performed. So I've identified some of the ways transient monitoring is used, but the list is only limited really by your creativity. Now I'll hand it over to Calvin to show you some real data taken from the field at these placements, lessons learned, and to suggest further considerations.
Great, thank you, Scott. Hope everyone can hear me. Hi, my name is Calvin. I will be covering a few examples of transient pressure monitoring. So the first example I want to show you involves comparing multiple locations with multiple devices. And to help you follow along, we've added these system diagrams at the bottom of each slide to show you the configuration, and the flow is going to be left to right. So the key to comparing data between devices is making sure the time on each device is identical. Transient pressure monitors use GPS for cellular, for time correction and calibration, just like many other smart devices. This particular example is a municipal potable water system. It's flowing downhill, and the color of the graph represents different pressure sensors. So the first sensor that we can see here, which is green, is installed at the top of the hill. This is upstream of the pressure reducing valve. The second sensor, which is red, that one's installed also at the top of the hill, downstream of the pressure reducing valve. And then the third sensor, which is blue, that one's installed at the bottom of the hill at the base of the surge vessel. So this is also all upstream of a fire pump. So looking at this graph, we can use this to calculate, for one, the pressure drop between the reducing valves, so that's between your red and your green. That's about 25 psi. We can also see the change in elevation between the reducing valve itself and the surge vessel. Upstream of that fire pump, that's about 43 psi, or around 100 feet. And so now let's look at the series of events. This first flat section you see here, that's going to be our system static pressure. And then we can see the downstream valve that opens and creates a large upsurge in pressure. And we can see how that surge vessel is accepting that energy. And then the fire pump stops, which creates another large upsurge in pressure. And again, that surge vessel is accepting that energy and keeping our potable water system within an allowable range. Okay, this next example is also a fire pump. This is a municipal potable water system. Our sensor is on the suction line at the base of the surge vessel, and the fire pump is started with no back pressure on the discharge line. So you can see at startup, the pump went off the right-hand side of that curve, which drained the vessel and also pulled a large vacuum on the suction line. You can see the pressure just oscillating rapidly as that pump is starving and trying to keep up. An important question to keep in mind here is how much back pressure is required to maintain the net positive suction head. And really, to eliminate this risk, the net positive suction head available should always be larger than your net positive suction head required. Okay, this example is a municipal potable water well with a vertical turbine pump startup. The sensor is on the discharge line upstream of the check valve. And you can see during startup, this pressure went way above 460 psi. This exceeded our system's maximum allowable pressure. And this is just another reminder of what can happen if your pump is started with no back pressure. You should also always keep your system's pump curve in mind. Let's see, if the air is vented out of the wet well column too quickly, this is going to cause a lot of damage. It's common to know your pump's operating pressure, but not many pay attention to the startup pressure here. Your steady state operating pressure for this system is only 85 psi, which is over 5 times lower than our startup pressure. This example is another vertical turbine pump, but it's in line with the flow. And again, we're looking at the pressure during a startup. The sensor is installed on the discharge line, again, upstream of the check valve, just like the previous example. And the data here is showing the high startup pressure, which lasts several seconds before reaching steady state. So this is unlike our previous example, which quickly peaked and then the operating pressure was much lower. Again, here the pump curve exceeds the system's MEWP during startup. And we want to keep in mind the overall system must be designed for the startup pressure on the left-hand side of the pump curve. This next example is the same system, but now we're looking at the pressure on the suction side of the pump. This is a good time to point out how beneficial it is to have multiple sensors installed. Some transient pressure monitors are able to show both sets of data together, and that's really helpful when you're analyzing and trying to visualize your system. So you can see the data here in blue. That shows a slight negative or vacuum pressure that occurred during that startup. The question again, does your NP-SHA meet your NP-SHR? The answer here would be no. We can see the supply did not keep up with the demand. This is a major concern for potential cavitation or vapor formation, and that's going to cause damage to the pump. There are several methods to preventing and avoiding cavitation, and transient pressure monitoring may help to confirm those decisions and the results. Okay, this example is a different system. We're looking at transient pressure data from another vertical turbine pump. This is a shutdown. The first sensor, which is green and orange data, that one is installed upstream of the check valve. And the second sensor, that's our blue and red data, it's installed downstream of the check valve. And again, this is a municipal potable water system. And some of you may know what happens when your pressure drops below the minimum 20 PSI, a boil water notice is issued. We can see that rapid drop in pressure to around 6 PSI before the pressure wave returns, and it eventually oscillates back to a safe static pressure. But something to think about when you look at this data is, what do your current regulations allow for this brief dip in pressure? And what's the length of time below that 20 PSI before the boil water notice should be issued? Some systems that only record once per minute or even twice per minute may have missed this. So you should probably just check with your local health official regarding the current regulations for your area. This example is a sewage or wastewater pump shutdown. We're looking at the pressure downstream of the check valve here. This sensor is installed on the combination air release / vacuum valve. And the data here is showing a low steady state discharge pressure. So we're just above 20 PSI. And when the pump turns off, the system goes negative. So this pressure drops fairly quickly and the system stays below 0 PSI. So this is revealing a few concerns. The first thing I would check is that faulty air valve because it never opened. It looks like it's clogged, or maybe it's offline completely because it was leaking, but either way, it probably needs to be serviced. The other concern is the system's minimum allowable pressure and even the risk of vapor formation. This is just a reminder, maintenance is usually cheaper than your repairs. This next example is a different system, but the exact same application and the sensor location. So the wastewater pump shut down and the sensor is installed on the combination air valve. Again, we're going to see a low steady state discharge pressure. This one's just above 10 PSI. And when that pump shuts off, the system goes very negative, minus 7.9 PSI. But take a look at the time scale on this graph. So most transient pressure data is shown in seconds, but sometimes you have to look at several minutes to see the whole story. This data is showing that air valve may not even be sized sufficiently. A vacuum was created after that pump was shut down, and it lasted several seconds, but the following oscillations were not as severe. Okay, this example is interesting because it's comparing data with and without a surge vessel during a pump trip scenario. So this is a high service potable water plant, and it has a very large centrifugal pump. The sensor is installed downstream of that check valve at the base of the tank. And we can see the data on top, which is without protection. And that went to 0, and it took several minutes to return to static pressure. And if we look at the data on the bottom, that's with protection, and it only went down to 50 PSI and returned to static pressure much faster. So it's just really interesting to see how the vessel was effective at giving energy into that system. It mitigated the low pressure during the same type of event. And this data can also be compared to your computer surge model and confirm your vessel was sized correctly and performed as designed. Okay, these next few examples are from a computer surge model that is simulating a check valve closure after a pump trip. And the goal here is to determine the check valve closing time. And we'll see how this relates to real data from an actual transient pressure monitor. So going down the list, the top graph, that's going to be our CV value or our flow coefficient. And we're going to see, it's going to show us when the valve closes. And it's difficult to see, but that vertical line here, it's not, let's see here. So it's not completely vertical, which means there's a length of time associated with it, and it's not just an instantaneous closure. That middle graph, that's our outlet pressure or just downstream of the check valve. And the bottom graph is our flow rate through the valve. So first look at the time scale. All of these events here take place in just 1 second. So we've got 0 to 1, and the graph is starting just after the pump trips. So looking at the data, we can immediately see the flow rate on the bottom and the pressure in the middle drop, which is our first step in the list. That's number 1. And this is what you would expect when the pump trips. The second step, that's going to be a brief spike in pressure, which we've circled, and we're going to look at closer on the next slide. But keep an eye on the time scale at the bottom, because all of those events take place in that 0.6 second window. Okay, so now that we've zoomed into that circled window, we can see this valve closes in just 3 milliseconds. That's 0.003 seconds. And keep in mind, we're looking at the data that's downstream of the check valve. And just before it starts to close, we can see our flow rate on the bottom is negative. So that tells me, 1, the flow rate is traveling back towards the check valve. And it also, number 2, helps to slam that valve shut. So you can see how the pressure is dropping during step 3 and then rises when that return wave closes the valve, which is our step 4. So now that we have this list to follow, we can use this to find the check valve closing time with an actual transient pressure monitor. So this data, this is a different system, but the exact same application we were just simulating. We've got a centrifugal pump. Our sensor is downstream of the check valve, which is in red here, and we're going to capture that closing time. So the first thing on our list is a pump trip, which is a fall in pressure. We're going to be seeing that here. The second step is that uptick in pressure, which is slightly cut off by this window. And then the third step is that downtick in pressure. And then number 4, that's going to be our rise in pressure or our check valve closing time. So if we took this window and we zoomed in further, we would actually see the time it took to close that valve. And that data can be used, again, back in your computer surge model to calibrate it and even improve your results. And our last example is just for fun. This is what happens when you start your washing machine. The solenoid valve that's on the inlet, it's going to open to let water in, and then it closes. So most people can hear the water hammer going through their pipes or in their walls, and this is what that actually looks like. And to make it more interesting, we've captured the same event at 2 different record rates. So channel 1, that's going to be our blue. That one was set to 100 times per second. And channel 2, that's going to be in red, only recorded once per second. So we can clearly see here which channel shows the whole story. You know, the high frequency data, that's channel 1. Our pressure went from 55 PSI steady state, we'll show you here, up to 80 PSI, and then down below 50. So if you look at just the red in that case, it only shows a 10 PSI increase, and it also completely misses the major parts of this event. So the point we're trying to teach is that transient pressure monitoring really does matter. You know, this scenario is just a simple washing machine, but it's creating water hammer. And just imagine you're doing any of the things on this list and you're only using the data in red, you're going to end up way off. Okay, so that covers all of our examples, and I just want to summarize with these 3 points. Number one, what is transient monitoring? Well, most pressure sensors record once per second, but transient pressure sensors can record 100 times per second or even higher. So it's really the high frequency part that's needed to capture these transient pressures. Remember that wave speed, like Scott mentioned, is faster than the speed of sound, and it requires hundreds of readings per second to capture. Number two, why transient monitoring is important. And for this, I want you to look at the picture on the right. This is another shutter speed example, like Scott mentioned in an earlier slide. If you take a single picture as this scooter moves past, you might just miss it. If you take 100 pictures as this moves past, then you get to see really the whole story of what happens. Without transient pressure monitoring, all we would know is that the pressure was at A and now it's at B. So transient pressure monitoring is important because it reveals the amount of time that these events take. And it also helps pinpoint your min and max pressures of each. And then let's see, number three, where to measure. So transient pressure monitors require physical sensors. These are connected to your system. We recommend using existing taps that have isolation valves. Reducer bushings, can be used, but for the best results, we really recommend installing the sensor as close to the source as possible without all of the additional branch connections. Generally, sensors should be installed on fluid-filled piping systems anywhere there's a potential velocity change. And that's the end of our presentation. Let's see if there's any questions we can answer.
Thank you guys so much. That was great. It was very informative. We do have some questions for you guys. So the first question is a three-part question. So is it always recommended to place the transducer sensors in between the components? How far from each other is it recommended to place the sensors to monitor water hammer, both between equipment or valves and along pipelines? And the last, do you want to answer those parts, or do you want me to also ask you the last part of the question?
I guess we'll stop in the middle there. So the first part was, is it always recommended to place them between your components? Not necessarily. This, it's not a permanent installation, I would say. First off, these sensors can be moved around. So if it's more helpful to have data at each location, we do recommend that sometimes. But between, your components is usually where you have an open tap or something that's easy to connect to. So that's generally why you see your sensors and transmitters installed in between your stuff like that. Scott, is there anything you want to add on where we see these?
Oh, Scott,
Scott.
Can you hear me now?
Yeah.
Oh, I was gonna say to add to that. I mean, it really just depends on what valve or component you're talking about. If you're looking at wave speed on a long pipeline, a little bit of distance here or there is not going to be a short distance on a really long pipeline is not going to make a huge difference. But sometimes, like Calvin was saying, on a component, we always recommend to put it as close to the component as possible, to really get the best hydraulic effectiveness, so that there's not a large pressure drop between the component and the transducer.
Okay, perfect. And so the last part of that question is, how many points of analysis are recommended for water hammer analysis?
Generally, I would say you would have to find a position or a sensor location on the physical system that you have in your computer model. So it's always best if you're measuring pressure, at the elbow of a pipe, that you have the same node in your transient analysis, so you can compare 100%, node for node. But again, it goes back to moving the sensor around. You don't have to collect all your pressure data at one position.
Scott, any other thoughts there? Okay, so there's another question. I have a hydropneumatic tank that has NRV on the main outlet and restricted orifice on the bypass. Should they install pressure monitoring on both the orifice and the NRV?
Scott, what are your thoughts on that one?
Can you say that one again? That was a little long.
Yeah. They have a hydropneumatic tank that has an NRV on the main outlet and restricted orifice on the bypass. Should they install pressure monitoring on both the orifice and the NRV?
Oh, non-return valve. So if there again, if it depends on what you're looking for. If you're looking to measure the check valve closing time, you would want to put it on both sides of the valve. But for the restriction orifice, I would think you would just put it on the upstream side of it, unless you're looking at the surge vessel itself, the hydropneumatic vessel itself. You want to verify that the restriction orifice is doing its job. You could put it on both sides. That. Do you agree, Calvin?
I would agree. And that's, one of the advantages of having multiple inputs to one of these devices. You can see both, at the same time.
All right, okay, so then the next question is, would it be best to do a model and then use sensors at the locations that seem to be problem areas?
This is a good one. I laugh because it's it's always better to design first and then and to come up with a solution rather than of course just kind of giving a best guess and then having to make expensive modifications after. But really it is ideal to do your hydraulic analysis with all the info that you have available, and then use your transient pressure monitoring to verify those results and make any tweaks as necessary.
They did clarify the model would be before the actual installation.
Oh yes, okay.
Okay. Any other thoughts on that question?
Nope, on my end.
Okay, so the next question is so the next question would be, can I use a surge wave in my 2000 plus PSI application?
Yeah, Scott, I'll go ahead and answer that. So there's many different sensors that can be connected to a surge wave. So as long as it has, the right input, there's devices out there that are voltage input or current input, but we do offer a wide range of sensors, and that includes your pressure ranges. We also have sensors that have either hazardous ratings or submersible ratings, but absolutely sensors can be custom ordered to 2000 plus pressures.
Perfect. The next question is, can transient pressure monitoring be used in lieu of my pressure transmitters and transducers?
That's a good question. So one of the advantages of our system is that it's not just saving your high-speed data. This device is constantly scanning and it's logging your low-speed, steady-state data, just like your normal pressure transmitters or pressure gauges are. So absolutely, this can be used in the same place your normal sensors would be installed.
Okay, perfect. Well, that does conclude our questions then for today. So Scott and Calvin, thank you so much for your time and your expertise and for being here with us today.